I'll work anything around. Okay, so we're talking about a few different, well, we'll see how many, 2 or 3 or 1 projects related to the evolution of gas giants that I've been thinking about in the last year. So one is with Chelsea Huang, who's a Princeton graduate student, and this project started off at the ESIMA workshop last summer, which I highly recommend to everybody that's in China. And we have an outcheck paper that came out over this summer on this. And then the other 2 pieces, I might not get to the third one, but they're a little bit more in progress and speculative, but I think it's good to show it here and it'd be good to chat to people here about them. So one's with a student of mine, Gabrielle Dominique Marlowe, who's now just moved to MPIA to work with Modicini and there in Hamburg. And then the last thing with Dublin and Domini, which I probably won't get to. Okay, so I'm not sure we really need this, but overall motivation, why we're doing this. There's obviously a lot of data on exoplanets now, and I just want to mention this point. We usually think it's an opportunity to learn about planet formation and evolution, but there's a lot of interesting physics issues in gas giant planets that have come up in studies of our solar system planets. And I made a list here, for example, of things like compositionally driven uninhibited convection, chemical separation, dynamo scalings, and how dynamos operate and so on. So one of the big motivations for this, for looking at extrasolar gas giants, is to try to use this new population we have to try to study some of these things. And, there's not necessarily a lot of that in this talk, but just at least to say that in I want to highlight three sets of observations which I think are interesting. And these 3 projects that we're talking about are related to these. So the first one has been around for a long time, the inflation of hot Jupiters. Hot Jupiters seem to have larger radii than expected. And there's a couple of trends. One is that the higher the incident flux irradiating the hot Jupiter, the larger is the anomaly, the anomalous part of the radius, the part of the radius that we can't explain. Actually, there's another interesting thing, which there's an interesting paper by Miller and Volkny. The ones that aren't too large, the ones that we think we can understand, have an interesting correlation where the more metal-rich ones seem to be a little bit smaller than the less metal-rich ones, metal-poor ones. And that's perhaps evidence that the size of the core, there's a core in those objects, and the size is correlated with metallicity. So there are a couple of interesting observational trends there. But the basic nature of this inflation here is still not really understood, and that problem's been around for a while.
When you say metallicity, you're referring to stellar metallicity? Or?
Yes. But then there are also a couple of emerging data sets. Okay, so one of them is directly imaged planets or brown dwarfs. And this is something that's starting to emerge now and will come online in the future in the next few years, hopefully. A sample of directly imaged planets down to perhaps Jupiter masses in towards orbital distances maybe 10 AU or hopefully below. And this just shows that from a recent compilation by Neuhauer and Schmidt, they looked for objects in the literature that are consistent with planetary mass. A lot of these are probably brown dwarfs, but they're consistent. Low mass brown dwarfs, but it's consistent with the planetary mass regime. And I think they have about 20 different objects here, a bit more. They're all large separations where it's easier to see the directly image and the contrast with the star. Okay, but this is sort of an emerging population, which I think is going to be very interesting because they're young, as I'll talk about. They're tied to the initial condition right after the gas giant formation. And then I think this is just something else to mention. The misalignment between hot Jupiter orbits and stellar spins has been found. And this is from the Albright et al. Paper that came out recently, so this is maybe the most recent compilation of this. This is the projected obliquity, the separation between the stellar spin axis and the orbital axis of the hot Jupiter as projected onto the sky. And there's this interesting trend here with stellar effective temperature. If you throw away the black ones, then you find that the ones with large obliquities, and notice that some of these are more than 90 degrees. That means the hot Jupiter and stellar spin are opposite. One is retrograde with respect to the other. And the ones which have large obliquities tend to be above a particular stellar effective temperature. The black ones here are either very low mass, very low mass stars. I think low mass stars. I think they have there might be a 0.2 solar. This is right. I can't be right now. Sorry. Maybe it's a very low mass. One of these is a very low mass companion. I think maybe it's 0.2 Jupiter masses and the rest of it. And then I think the other two are have orbital periods beyond 7 years. So they're trying to make the point that there's no way that tidal evolution can be affected too. ones that are arguing have been entirely, people who use being entirely counted.
Isn't AG successors known as quasi-1 that everyone believes it's, if anything is showing the quasi effect, that's the one. So then it has 4 degrees, that's a smooth quasi integration.
That's, yeah, it's a very eccentric one. And, all I
So
see is
currently-
this measurement here is like the critical cosine.
Currently, periapse is smaller.
I hadn't noticed that, yeah, so that's the same, that's the cosine critical angle you're saying. That's interesting. Has anyone pointed that out?
No, it's
Before? Yeah, okay, I haven't seen it. Okay.
actually normally would take it.
Yeah.
No, I mean, you're saying that the measured angle here
Yeah.
looks like 42
And that was
degrees.
supposed to be considered a success for the cosine.
I see, I hadn't appreciated that point.
They could be wrong.
Okay, so there are 3 things. Moment heating and Jupiters I'll talk about a little bit. Evolution of young gas giants, and there probably won't be time. If there is, I'll just talk about some speculations about magnetic interactions. Okay, so ohmic heating. So here again is this radius anomaly. And here's the plot from the recent paper by Laughlin and they et al. And they fitted the radius anomaly as a function of the temperature of the planet, so the radiation temperature of the planet, and they found this relation here. And it was realized some time ago that the one way a generic way to explain this is to deposit about 1% of the radiation. So I take all the energy coming in through radiation, and I deposit about 1% of that somewhere fairly deep in the planet. It has to be towards the near the convective radiator boundary. And if I do that, then that's the power I need to be able to delay the cooling of the planet and keep it inflated at the observatory. Yes. Sorry, yeah. So the idea is I take a model of a gas giant with the right level of radiation, and I evolve it over time to its current age, and I look at what its radius should be, and I compare it to the observed radius, and I find the observed radius is larger, and the amount by which is larger is the anomaly. So this is actually in Jupiter radii, so this means that the subject here is 0.4 Jupiter radii larger than the should be.
And how much is that evolved radius, model radius, bigger than the perfectly cold radius of the planet? You could just let it cool up and cool it. Is it any significant difference between those two?
There is significant difference. Yeah, the radiation can raise you by 1.2. It depends on the temperature. It does make a big difference. It delays, as I'll talk about, it delays the cooling. It keeps it slows down the cooling rate by moving the convective boundary around, and so you stay with it. But that's not enough. That's not enough to explain the society's anomaly.
But also, here this number of them are too small.
Right.
It might need to believe. Yeah, well, it might need to believe their error bars are underestimated.
Well,
that's a correlation with not the planet temperature, I would say. You could also then believe that.
Well, so the way they say in this paper is that they put in, they look for a correlation and it reduces chi-squared significantly, but it doesn't reduce it to the unit. So it's clearly scattered up around the relation. But for example, there are ways to, yeah, go ahead. Well, there are ways to scatter, I mean, there could be other things going on, for example, the core is not these things.
And of course, at a temperature of 0, it's a radius of 0 degrees, so there must be something wrong there anyway. Rather unphysical, I think, actually.
Within this range. Okay, so a few mechanisms have been discussed, but one that's gained recent popularity is ohmic heating. And just so let's talk a little bit about that. So Backman and Stevens in 2010 have a paper, and actually it still goes back to this paper. I think it's Lou. I think I have the right author here. Stevenson and Goldreich for our Jupiter. They asked how deep can the zonal flows we see on Jupiter? How deep can they penetrate into Jupiter? And they had a constraint because if the zonal flows penetrate too far in, you shear the magnetic field, generate currents, and that will cause ohmic heating. And we don't see the evidence of that ohmic heating, so we see ohmic. And the idea is to do something similar here for a hot Jupiter. So the idea is I have this flow, I have some kind of circulation around the planet. Imagine, I don't know, this is the day side, and this is the night side. So the star is illuminating the day side here, it's tidally locked. And then I generate a flow around the planet. And as that toroidal flow moves, it shears the toroidal field lines. And as I shear the toroidal field, I generate a toroidal field. The toroidal field has an associated toroidal current. And what they're showing here are these closed colloidal current loops. And the idea is that by sending in this colloidal current, you give yourself a way to heat the interior of the planet, because I have ohmic heating associated with that current. So just J squared over sigma. And it's around about basically at the same time, Perna, Manu, Versha were working on a couple of papers, and one of them was looking at drag on hot Jupiter, on the flows in hot Jupiter atmospheres. There can be magnetic drag from this shearing, and also heating rates, very similar in heating rates. And I show here a plot from the Perna paper showing as you go down in pressure into the planet, the convective boundary may be around, depending on the evolution, but around 100 bars or something. So this is quite far down, showing the cumulative heating rate that you can get. And you can estimate this, so back at the envelope level, just to convince yourself that it doesn't make sense, that perhaps you could get enough energy. So the idea is that if I have a dipole field, B dipole here, the toroidal field that I induce, that's the little b, the toroidal field compared to the colloidal field is just the magnetic Reynolds number. So it's just this calculation where I shear the magnetic field lines and they're diffusing back via ohmic diffusion. And once you've got into that equilibrium, then that's the limit there. So the question really is, how large can I make this magnetic Reynolds number? Is one question in this wind zone, and that sets the toroidal field strength. And if you want to estimate the current going in, it's going to be curl B, so it's V phi divided by R, the radius of the planet, roughly. And then you can just ask, as I go in, what's the ohmic heating rate per unit mass? And then you can also look at the total ohmic power. And an important point here is that this heating rate drops rapidly as I go into the planet. And that's because the conductivity, well, first of all, obviously the unit mass is going to be dropping, but it's really that the conductivity rapidly increases when I go into the core of the gas giant. And so that means that the ohmic heating rate goes down. The ohmic heating is much, much stronger at lower density. And so that means if I want to estimate the total ohmic heating rate, I can look at the power, the ohmic power at the top of whatever region I look at. So I look at the convection zone, for example, I look at the top of the convection zone, the lowest pressure, and I can just multiply the ohmic power there by basically the R squared times the scale height. And that gives me a good estimate. And the key thing is that because the ohmic heating is volumetric, it's J squared over sigma per unit volume. If I want to know the total ohmic power, I've got to take the power per unit volume and multiply by a volume. So when I multiply by a volume, I multiply by a scale height, h. And that scale height goes like 1 over gravity, or 1 over mass. So what you find is that this ohmic power very simply scales like 1 over mass. If I keep temperature the same, the irradiation temperature, for example, and I double the mass of the two Jupiter masses, the ohmic power will go down by factor 2. It's just a volume. And we'll see that in a minute, yes.
An idea that you have one magnetic field, you scale everything to 10,000.
That's right, yeah. So I'm choosing, so there are various arguments that you can make. So for example, one argument is that you compare the kinetic energy convection as soon as in equipartition with the heat field. So there's a recent paper at Glasgow where they argue that this scaling holds over a whole range of objects from normal stars all the way down to. And then there are older scalings, Stevenson text scalings from the 80s where you Alsace number with the omega, that you're bouncing Coriolis forces against the magnetic drag in that case. So there's a scaling there involving omega. So you can use either of those. If you apply those to the hot Jupiter case, you find that these numbers are reasonable. So that's what they come from scaling arguments, and there's no observational evidence that those are right. So
Somebody looked at Jupiter, our Jupiter.
but we're scaling from our Jupiter.
Not just Jupiter hat, just for reference.
One. And this number here is in the realm of what we need to get the hot Jupiters into the especially given the freedom. If I go to 100 gallons, for example, I can reduce this to 10 to 25 burners per second. So there's freedom here in these parameters, but the numbers are not crazy. You look at this and you think, okay, maybe there would be enough power here to do something interesting.
Well, yes, hold on. You changed your conductivity from 27 to 10 to 6 to 10 to 5 in these scales.
You're right, isn't this incredible?
So, I'm getting worried.
Let's stick at the top.
Yeah, there's a redshift going on.
Are you going to explain this?
I will indeed. I will try my best. I mean, the truth is that the conductivity is the most uncertain parameter here, or rather the parameter that can vary the most. And the reason is that the conductivity here is believed to be dominated by alkali metal thermal ionization. So it's Saha type, it's very sensitive to temperature. So that explains why in different formulas, which I've pulled from various parts about the paper or something, that's why I have different values. Okay.
I trust you.
But just trust me, I'm just trying to give you a sense, I guess, of the back of it. In reality, the temperature of the atmosphere is crucially important because it sets the conductivity from this very sensitive temperature. Yeah, I'm not trying to hide that, and if anything, I'm glad I highlighted it here by choosing this range. That's good. Okay, it's okay. So there were two papers I want to mention. So one is back in series in 2011. What they did here, with Bodenheimer. And it's Bodenheimer. So they take numerical models of gas giant evolution from Bodenheimer and put in some ohmic heating and evolve them in time. But the previous paper was steady state models, so they're just asking the question, is there enough power here to do something? But here they're actually calculating the evolution in time. And this shows you various planets with various effective temperatures and various masses. And you see there are various behaviors, including these curious solutions where they get evaporation, they get runaway heating, and the radius of the planet is increasing and actually running away.
That's the arc of the force in your other equation, right? So there's a vector reaction there. You got a bigger increase in power.
That's true. That's true. That's true. For constant, everything else.
Well, the T is a constant.
But I think the point here is that there's other work in which this does not happen. And so, for example, there's a photo of Yanchin paper with Yoram, came out this year. And in this paper, this runaway heating is not found. Actually, in this paper, there are a couple of important points. So one is the importance of the wind zone depth. How deep you make this wind zone can make a big difference as to how much energy I can end up depositing in the center. No evaporating solutions. And an aspect of both of these papers is that you can explain the observed hot Jupiter radii. So here's the back again series of Bodenheimer plot from their paper. They're showing observed objects versus various results from calculations. And you see that you can explain the observed radii if I put in an ohmic power, which is a fixed efficiency, 1% or a few percent of the irradiation. So that's the assumption here, that that efficiency is constant and maintained during the entire revolution. It's always 1% or a few percent. And if that's true, I'm guaranteed to deposit enough power to explain what the radii will see. So the calculation they do is detailed in the sense that the electrical conductivity is calculated very carefully and the power distribution is calculated very carefully. But the overall scale of the power they're putting in is just scaled to be 1% of the radiation for the whole thing. And I think it's fair to say that in Wood-Ludwig that's also the case, right? You're basically saying, yes, you can explain the OWs, but again, it requires a sufficiency of 1%.
So to do better than that, you have to calculate the zone winds as well.
To do better than that, you need, yeah. So I'm going to show you a crude attempt to do better.
Well, the new company does that, right? They try to calculate efficiency as well.
That's exactly right. Yeah, that's right. So Manu has an atmospheric a wind zone model which I'm going to use here, and in that paper he's talking about, well, it looks like the drag from the magnetic field is enough to reduce the efficiency. And what I'm going to show here is a calculation where we try to put that into the evolution.
So I guess what we say is the efficiency. Well, if the wind zone only goes down to 10 bar, then you need certain efficiency.
Right.
But the efficiency can be reduced if there's a bigger wind.
That's right.
But the question is that in a low and slow calculation, when you figure out how deep the wind goes.
That's exactly right. Yeah. And it's very difficult because, for example, in numerical calculation, it takes a long time to get into equilibrium at that depth. It's hard to, you can't run the calculation long enough to get into equilibrium.
That's right.
So there's still not, the
so
conversion
that
of those ratios, that's right. So that's a big uncertainty which I'll highlight here. So what we try to do is just something, let's try to separate this problem into an easy part and a hard part. Okay. And the idea is to think about the wind zone interior separately. And we're going to replace the wind zone by a boundary condition. And the spirit of this is thermal evolution of gas giants. So when people calculate the thermal evolution of gas giants, what you often do is you replace the outer atmosphere by a T effective T10 relationship, where T10 is the temperature at 10 bar pressure. And that's just your boundary condition. You do that calculation separately. And you just use that as a boundary condition for your evolution. Let's try to do the same thing, but now choose, for example, current, or we're going to choose the V5. So we're going to parameterize our models in terms of temperature and V5. And by specifying V5, what really means we're going to specify current in this way. So there's a unique correspondence. And once we've got current, we know the heating rate. So we're really specifying the heating rate, but we're going to encode it in V5. And the idea is then we can then do some parameter space study of the evolution given B and T. And then the wind zone model will feed in afterwards, and we'll try to figure out what does the wind zone models tell us about where we have to live in that parameter space.
Kristen sort of made a point that the heating actually affect T sufficiently. You guys have got that?
We don't. So yeah, what we're doing is we have to map the irradiation temperature to the temperature of 10 bars. So the way we do that is to use a non-magnetic field heating. We use EO, just one of them, EO and moving models for that. So that's, but I'll argue at the end. I think I'll show you how that would affect our conclusions at the end. Okay, so just a reminder, how do you do this calculation? Well, here's a way to do it. So there's a nice description of this following the ADFS approach in Harrison Goldstone 2006, and I thought I'd use that plot. It's a very nice plot. So if you think about what's the thermal structure of a gas giant planet, well, it's mostly convective. And so if you look at the internal structure, from the central pressure outwards, you're following an adiabat, some entropy. And the labels here are entropy in kV over MP, so 1097. And eventually, in the very outer parts at low pressure, you join onto, for an irradiated planet, you join onto essentially an isothermal outer structure, which is set by the radiation. Or for an isolated planet that's just cooling, there might be some radiative atmosphere here that you join onto. But the idea is that for an irradiated planet, say, I fix the outer temperature, for example, here 3000 Kelvin by irradiation, and then over time what happens is that the entropy of the interior just drops as the interior cools. So the time evolution is just to go from one entropy to the next with a constant outer temperature for an irradiated object. And that means that if I can make a sequence of, I should say, sorry. So if you think about what are the parameters to specify the model, one is the irradiation temperature, one is the adiabat that I'm on, the entropy of the interior, and the other part is just the mass. And what the mass does, at a given entropy, the mass just changes the central pressure. So different mass planets just have a different central point here, but always on the same adiabat. Okay. And what's nice about this point of view is that what I can do is I can just make a grid of models over mass and entropy, make a grid of models, and then to do the time evolution, all I have to do is step through that grid. I don't have to do a full style structure calculation, I just step through the grid. And the reason is that the convection maintains the adiabat, always constant entropy, and I can effectively do a one-zone calculation. I just integrate like this. I just say that the luminosity of the star is decreasing the heat content of the convection zone. And so by finding an appropriately average temperature over the convection zone, I can just follow the SDT as you move from one adiabat to the next. And the luminosity is given by, for any given model, the luminosity is given by the radiative luminosity right at this point here where I go from being convective to radiated. At that point, whatever the radiative luminosity is there, that has to be the luminosity of the object. And so given that luminosity, I know how quickly the core is losing heat, and so I can follow how quickly it moves to lower entropy.
How do you deal with the two sides, or are you just assuming that this is circularly symmetric?
You can assume circularly symmetric. So at the end, I'm going to have a big list of questions. So there are interesting things to think about next. Let's just do the simplest case first. And actually, I think this goes back to the evidence in 1977. That's the first place I could find this stepping through adiabats kind of approach. And it does remarkably well if you compare with the time-dependent calculations. I'll show you that later. Okay. So now let's try to add only heating and use the same approach. How would we do it? Well, the first thing is, imagine if there's only heating inside the convection zone. Then the way I can add it in is to say, I know the luminosity leaving. That's made up of the SDT, the cooling part, but also now I have another contribution. So for a given model with entropy and mass determined, I have the structure. I could just go in and calculate the ohmic heating in that convection zone, and then I add the ohmic heating into my evolution like this. And you see there's an opportunity here to have a balance. As I evolve over time, I can get into an equilibrium, potentially, where L is completely made up of ohmic power. And that would mean that the planet stops contracting, because I'm just feeding in all the luminosity I need, I'm feeding in from ohmic power, and I no longer have any contraction.
Well, it does not depend where you're feeding it. I mean, you don't have an AU atom if you're feeding it to someone. You don't have convection.
So the assumption is that instantaneously any heating in the convection zone is thoroughly mixed. But if I heat right at the top, I will change the position of the radiated convective boundary. So what I'm trying to do is separate those. I'm just going to separate it. I'm just sort of writing it down and separating it in two pieces. But the second part here is exactly what you say. It's that if I'm heating so much that I significantly raise the temperature of the part above the convection zone, I have to self-consistently solve for the new convective boundary at each step. But I can do that given the V. So if I know mass, entropy, and now magnetic field, which tells me the ohmic power, I can self-consistently calculate the structure of that planet instantaneously. The instantaneous structure.
I guess he's worried about that if you raise the temperature enough, you go sub-85.
Yeah.
And just halt the convection.
But as long as that's happening, as long as that increase in ohmic power is happening on a long time scale compared to the thermal times involved, the overturning time and the thermal time of the outer zone, then I think it's okay to do that.
What I'm saying is, I think that if you went to this terminal state where all the luminosity comes from the heat, and you have a problem there, can't be any direction in that terminal state because you have to be.
I agree. So what we're going to do is we're going to evolve to a state where maybe the ohmic power is a third of the luminosity or something, and then we'll stop. Okay. Yeah. Because as you say, after that you have to shut down convection. And the evolution time becomes very long. And so what we're going to say then is that you've reached a final radius. That's exactly right. But up to that point, then it should be appropriate. So what that means is I could just make a big grid of models now, and it used to be just M and S. But now I make a big grid of gas giant models now also with parameters B and then temperature. Okay? And then once I've got my grid, I can just step through into any evolution I want. Okay. But one point I want to make is that I don't have to do any time evolution. And let me just show you that first. So here's, well, let me make a point about electrical conductivity. So of course you need to put in electrical conductivity. This is the conductivity due to electron neutral scattering, and the electron fraction here is going to come from alkali metal ionization, thermal ionization of alkali metals. And I just want to make this point here, that if you look at the Badigan and Stevenson's work, at least in the 2010 paper, they happen to have chosen a different sigma and a different V. And what they're doing is they're assuming that the sigma is just pi r squared for the hydrogen molecule, and that the V is just the mean for a mass Boltzmann distribution, just the simplest thing you might do. Which sounds harmless, but it turns out to give a conductivity which is 9 times, factor of 9 different. So if I want to really calculate, without assuming an overall efficiency, if I want to calculate the evolution, I've really got to worry about these factors and get these details right. If you're always going to scale the power to be 1%, you don't care. But if I want to self-consistent calculate, I've got to get it right. Right, so what does this look like? So here's luminosity in solid lines and ohmic power in dashed lines as a function of entropy. And one point I want to make is that you don't have to do time evolution to get a sense of whether ohmic heat is important for these planets. What I can do is just look at this plot. Because for a given hot Jupiter, I know its mass today, I know its mass, and I know its radius. And I know it's how strongly it's being irradiated. So what I can do is, I can ask what entropy must that planet have today to match the observed radius? So I just go through all the hot Jupiters and calculate what entropy must they have today. And that allows me to put them on this plot. So imagine I have an object which must be sitting at entropy 8.5 to have the radius it has. And I look at this plot and I say, okay, well, if B is, here we assume B equals 100 Gauss. If B is 100 Gauss, and I'm sitting at 8.5, there's no way, depending on the mass, there's no way for any of these masses here for ohmic power to be a large fraction of the luminosity. They're off by 2 orders of magnitude. If I wanted to make the ohmic power large enough, I'd have to have a B field of 1,000 Gauss. And so it immediately tells you a mapping. You can just look at all the hot Jupiters and figure out what B fields in this language, what B phi do I need to have ohmic power matter today. So that's what we did. And here, I'll just show you what that looks like here. So what I've done here is, here's the V5, and then each of these data points is an observed hot temperature as a function of the equilibrium temperature from the radio radiation. And this shows you, ignore the lines now, I'll get back to that. The points show you the V5 that you need, or in other words, the only heating level I need to explain the radius here. And I just thought I'd show this if you, this is the convective pressure, the convective boundary pressure. And usually as the planet evolves from high entropy to low entropy, the convective pressure, the convective boundary moves to higher and higher pressure as the adiabat drops to lower and lower adiabats. And what you see here is that the B field has a really significant effect. If I have a lot of overheating, 100 Gauss level, then you very quickly push the convective boundary really deep. And that delays the cooling. It's really important because when I push the convective boundary deeper, the luminosity of the object, which is set by that boundary, drops dramatically. And you see that in these plots here, that as in this plot. So you take the blue curve. As I go to lower entropy, this is fairly constant, but you see how it starts to dip here, and the luminosity starts to dip, and that's because this effect, the heating outside the convection zone is becoming really important, and it's pushing the convective boundary. All right, so we can now do time evolutions, and so for example, this shows you what V5 do I need at a given temperature, how much magnetic field do I need, depending on mass, for ohmic heating to be important to 3 B heaters, for example. So we can explore the parameter space like this. And then the question is, these aren't really independent parameters, they're determined by the wind zone model. So then we can try to look at that. So what we did is to look at Manu's work recently. It's not the only one I can discuss this, but Manu writes down, based on some evidence in Shulman and Manu, that book chapter 2010, this balance here, momentum balance around the equator. So the idea is I have some equatorial jet, and this is a thermal wind kind of balance, where I have a temperature gradient from day side to night side, and that temperature gradient is causing a shear in the vertical direction. That's this balance here. So I have V5 divided by a pressure range, that's the vertical shear, and then delta T over R is the horizontal temperature. And then the idea is you mess that up with magnetic drag. If I put in a strong enough field, I get this magnetic drag term, which can mess up that and interrupt that thermal wind balance. And so there are various regimes at low temperatures when the conductivity is very low because the ionization level is low. Then this term is not important. And then what happens is that as I increase temperature, I get more winding, more velocity, more flow, so more winding in the field, and I get a larger V5. But eventually, when magnetic drag kicks in, I limit the V5 I can make, and it saturates. And this difference here is the thickness of the wind zone. So in this model, as I vary this thickness, delta log P, I vary the vertical gradient here in the velocity, and then I end up getting a shift in V5. So the idea is let's take this very simple scalings here, just momentum balance kind of scalings, and use that to calculate V5 as a function of T, and now see where we are in terms of the Hutchins. So this shows you some results here. So here I've got radius against temperature, radius against mass, and radius against temperature. And then here's the observed over the predicted against temperature, and the observed over predicted against mass. So they're equivalent panels left and right, but this is a ratio, and that's the actual radius. And the message is that there are quite a few which lie above the line, which means that we can't explain them. We have much larger observed radii than the predicted ones. And to get a sense of why that is, I think it's good to go back to the other plot, this one. And on this plot, I put the solid line here is the V5 from the wind zone model. So you see that it's rising and then saturates. And the simple argument I had before nicely divides actually from the time evolution. So when I do the time evolution, I get roughly the same answer as the simple argument. And the way to see that is that the black ones are ones that we could explain in the time evolutions, and the red ones are ones that we can't explain in the time evolutions. And they seem to lie on either side of the V5 that comes from the wind zone model. So if the wind zone model is producing a V which is larger than the required value, I can explain it. If the wind zone model doesn't produce a high enough V, I can't.
But wait, doesn't the saturation V5 depend on the background photo field?
Yes,
This is BR, B5.
that's this. Yeah.
Ah,
1 Gauss, 10 Gauss, 100 Gauss.
so you're still out of luck no matter what you choose there, because they're going to choose the right
Saturated.
We still have
I guess my point is that you can't fill up there, no matter what you do, right?
That's right. Well, perhaps it's something we can do, which goes back to Norm's question. Because what we're assuming here is that I'm assuming TEQ is, I multiply this number, this is stuff by the irradiation, I multiply this by 1.33, which is from a standard no heating atmosphere. And then I get my T10. So if that number became 2 instead of 1.33 or 1.5 instead of 1.33, it would shift all of these points around. So I think that can help.
If you say that,
Sorry. Say that in English there more slowly. So yes, okay, so we are saying, so T10 is the temperature at 10 bars, and that's my outer boundary condition for my evolution. And I'm saying that's equal to 1.33 times this equilibrium temperature which comes from irradiation. And this number here, 1.33, comes from doing an atmosphere model, actually an analytic version of that atmosphere model, and that gives you that number. So particular choices of opacity ratios and so on. So observations tell you this number, but our models require a temperature of 10 bars, so I have to get this number and then recall that. Now Norm's asking, there's going to be only heating in the atmosphere, a lot of it, and because it's low density. So what's that going to do to this relation? It's going to do something. And the answer is we don't know what it's going to do. But if this number changes, what will happen is that all of these points would shift. Because I have a different multiplicative factor.
Observed bunch.
horizontally or vertically?
So what I'm doing is, right now, let's shift the lines and not the points. Should we do that? So if I want to shift the lines to the left, then I need to make this observed temperature hotter at 10 bars. So I need to increase its number, which makes sense. So it does go in the right direction. It goes in the right direction, and you can move this over. However,
You can move it enough, but then you need a low magnetic field, otherwise you still can't do it, right?
I can't, exactly. Then I start getting the problems with these. There are still some that I can never quite get.
No, but you also need to move it a lot. With the low field is the case where you wouldn't expect to move it that much.
Well, the other thing is the connection between the pressure or the temperature at 10 bars and the temperature top. You have the same problem with the sun, right? You don't treat the top layers of convection. So there's usually a big superadiabatic gradient there, which is not modeled at all. It's just it's sort of measured. And that will kind of make that number bigger.
But if you still
Although
get
the
the same
convection
ratio.
zones are well below 10 bars, well high pressure. The convection zone is deep.
Well, okay, so how
But
far?
once you get to low entropy, it's deep.
How deep? Way below 10 bars?
You have to sort of go back to that plot. I mean, there's a lot of range there. You can see here, so here's 10 bars. So if I'm in an entropy of 9, I'm basically there. But once I get down to 8 or 7 or 5, we want to hold the contraction somewhere here, depending on the object. Then it's
And this is also somewhat unpleasant that, so if you seem to always need a small colloidal field, you then need a D5, which is 10,000 times bigger than it. It seems sort of becoming, at some level, becoming unreasonable. If you're feeding something that huge with something that small. But if you take your most lowest points, right, that never changes.
the Reynolds number becomes huge. Yes.
Well, remember that when FIRS is the base of the solar convection zone, and it goes to perhaps 10,000 Gauss, you know,
Well, higher.
1,000, at least 1,000 times, 2,000 times the dipole.
That was like 1. It is true that once the ice, you don't really know.
Yeah,
In a short.
but yes, that's where you have tons of energy available. You're not in a wimpy atmosphere.
Okay, so I think what's happened here is that this highlighted exactly.
What are your betas actually?
These questions that you're asking, exactly. It's, what are the betas? So for example, if I go to a pressure of 10 bars, pressure of 10 bars is 10 to the 7 CGS.
Oh, that's getting tough.
Okay, it's getting
Yes.
tough, right?
Okay.
So there's a whole bunch of, so I think the calculation we've done is very simple in many ways, and it's, very simple, we can place the outer zone by boundary condition and so on. But I think it highlights what are the really important pieces of physics that we need to go in and look at. So for example, what's the thickness of the wind zone? What are the dynamics of the wind zone, even in terms of day-night side asymmetry, or how do I exactly break this thermal wind? But I could in Stevenson have a different thermal wind which is in the latitudinal direction rather than around the equator, and they break that. So nobody's looked at a model where you combine those two, for example, just in a simple way, not necessarily doing an numerical simulation. How much toroidal field, how big can I make RM, data and so on. Coupling between the wind zone and the efficiency, oh, well that's just the point that it's actually hard to calculate, so we keep asking ourselves, how do I relate this to the overall efficiency? But I think the key point is that the wind zone model you use all changes that. Whatever I do for the wind zone changes the ratio of ohmic power in the wind zone versus inside the planet. So then it becomes really hard just to talk about efficiency. You can't just set a number of 1% without knowing what the wind zones are doing. Okay, so there's a whole bunch of possibility of feedback to the dynamo. If I send strong currents down into the interior, how's it going to affect the dynamo?
Let me make sure I understand the practice.
Yes.
So it's Martin's asking, right? You've got a wind going around the equator. So you know what rho v squared is for that wind from the wind model.
Yeah.
And when you're assuming that presumably you can't have v squared be much bigger than that. And the idea is that it's comparable to because you're assuming sort of that or the models produce that.
It's really this drag term is shearing the field until diffusion balances.
That's what I'm saying.
Shearing
That's
it,
what I'm saying. Right. You're balancing.
You're assuming you have time always to get into the induction equation equilibrium. But then you put that into the momentum equation, and that's the balance that you end with. So it's the driving balancing the magnetic drag.
But you're calculating in those models, right? It's got to be calculating the force exerted by the gas on the
You assume it's completely coupled. Well, sorry, there's only diffusion. There's an eta.
right.
But otherwise it's fully coupled. So it's the energy limit, but with the eta.
So then there's questions about like, what's the filling factor? It's really tight bond. It's not help that which is what you see in the sun.
Well, I hear the resistivity is high enough. It probably won't be tight bundles.
Well, the resistivity of the sun at the surface is all that. Right? It's pretty
But in the sun, it's the convection that organizes this into the windows.
well, it's not clear what it is. But there's convection. It's not gravity seems to be that. It's spread out, it seems to get out.
Okay, so I have 10 minutes, so I'm back in this. I'd like to say something about material now.
So what's your bottom line? Does it work?
No, well, the bottom line is I think that
That plot there, which kind of would be
the bottom line is this plot,
Yeah.
and it's that you really have to push this with these Reynolds numbers, even if you're allowed to shift this over. So one thing you can say is let's just tune the wind zone model so it makes this line match the data. But if I do that, I find I have to have huge Reynolds numbers. It's really hard to get. So there are some objects where we just can't do it, and then the other objects I have to.
So the bottom line is that in the layer of the atmosphere, we think you do have a wind. The conductivity is high enough to entrain a magnetic field and heat that layer.
Yes.
I mean, and then how sufficient is that? This is what I remain confused about this whole thing. How sufficient is that guaranteed heating to feed back on the structure? I mean, do you need to yeah, then what's happening in that wind zone? Or is it just the local heating in wind zone is enough?
It's the deep heating you really need.
Okay. Then how
Because
certain is
you're
that
halting
deep
the
heating?
you're trying to halt the contraction.
Yes.
So you have to push the convective boundary in.
Right,
And
so
you do that by
how
heating
certain
it
then is
until
that
it's
deep heating given that you have this more superficial layer that's entraining the magnetic field?
how sufficient?
How certain is that
How certain is it?
deeper heating?
Well, if you give me a magnetic Reynolds number in the wind zone, if that implies a flow of current,
Yeah.
then
Just send the current down.
you know, if that's true, then you assume, and if you're happy having alkaline level thermal
And you know what the
ionization,
run of the
and if you know the alkaline level abundance, and there's nothing messing up the electron fraction, then it's a very straightforward calculation. So that's the reason we did that part, and we did that part.
So they're claiming that it's really guaranteed to be a certain amount. It's just almost 10 milliresistive.
So if you could mess up the electron fraction somehow,
Actually, in the deep region where the heating is required to happen, it's actually not alkaline level. We transition to the type of hydrogen
quite deep though,
by about 10,000 bar, 100 bar. That's where the heating is.
not 100 bars.
Right.
Well, we can look at the conductivity base.
Right. So just to put it in another perspective, the way I think of it is that those really large planets, they are about the size when they were just born. They are about the size when they should be less than a million years old, which means the luminosity coming out of them, even their size, the luminosity coming out of them is so huge. I mean, something like 20% of the solar irradiation on top of the planet has to be converted into internal heat.
So that the 1% number is only for solar planets, you actually.
Yeah, one day only, well, I was using 2% so who knows. So majority of them is consistent with a few percent if you assume a shadow window. For the really large ones, you just have to convert all the radiation levels, maybe not 100%, but 20-30% into the deep region. And that seems very difficult to convert.
For example, the
There's
one
one
that's 1.8,
there was
1.8
one
Jupiter
two,
radii.
1.9, 2 Jupiter radii. That's the size they have at 1 million years old. And I just want to see how old it is.
So maybe I could move into that actually. That's okay, just 5 minutes. Just to show you. So something I've got Gabrielle's work here on on isolated. So we've done some stuff on isolated cooling gas giants recently, and I think there's an interesting physics question to pursue here. We haven't really got that yet, but I'll just show you what we've been doing. So there's this idea that was sparked up by Marley et al. 2007 about hot star versus cold star. And the idea is now to not worry about hot Jupiters, but let's worry about Jupiters which are very far away, say 10 AU, 100 AU from the star. They're just born and they're cooling over time. The question is, what initial conditions do I put in for the Jupiter that I make? And Marley et al. Took, again with Bodenheimer, Lissauer, they took core accretion models, and here's a standard luminosity track from a core accretion model. So during this phase here, when it's very bright, you're building up the Jupiter by accreting Jupiter masses worth of material to build up the gas giant. And then at the end of accretion, what they found is that depending on the mass, you plummet down and you reach some luminosity here, and you calculate the internal entropy of this object. So in other words, they're taking the best core accretion model they have, they're making a gas giant, and they measure its entropy, its internal entropy. And what they found is that the internal entropy is a function of mass. It looks like these black dots here. So it's around between 8 and 9 as a function of different masses. Now, what people have been doing previously, whenever you think about an isolated cooling gas giant, is doing a hot start. And a hot start means that I just make the planet arbitrarily hot in the beginning, so that it just cools onto a standard cooling track, and you forget your initial conditions. If you're hot enough, you just go onto the standard track. But the point here is that these are a lot colder. They're much lower entropy than the hot start models. And so they start off actually hardly evolving at all. They're going to stay at this luminosity for a while, and then they're going to join the cooling track much later.
Are they basically colder inside than they're outside?
Then, yeah. Oh, sorry.
Because their pores formed first is not all that warm. You treat them and it's actually warmer.
Well, I don't really understand this result that comes out of the simulation, so that's something that I think I've tried to understand this result. You know, what determines these
really waves a bit. I mean, that sounds like sort of a newly formed neutral star. So there's something else in the interior happening, and what you see on the outside doesn't really matter. And in this case, the only thing that could be, I guess, is sort of thermal readjustment in the interior.
So the story they tell is that in the boundary condition they have is a shock, a radiative shock. So they assume a spherical flow in their calculation, and then they write down some boundary conditions which are the shock. The idea is that at that shock you radiate away all your gravitational potential energy, accretion energy. But if you look at that shock, try to calculate the entropy of the material, it's actually very large. It's sort of up here. So I think the answer lies in some kind of settling solution or something. There's some kind of settling of material below the shock.
Well, it must be the core itself, right? So what is the specific entropy? Is it average over? Is it right in the center, or?
Well, the core is fully convected. The core is convected. It has a well-defined entropy in these objects.
Okay, so they have mixed in the metal, original metal.
Yeah, everything's mixed up.
Okay.
Most of the masses are. So again, it's an interesting question here. You know, why is this? What determines these entropies? Are they robust? What if I change my core accretion theory a little bit? Is this a robust prediction of core accretion or not? And that's the question I'm really interested in, and that's the question I haven't really made a lot of progress in. But I'll show you what we have done. So again, we've done the simple part. Oh, and I should say, people doing direct detection experiments, direct imaging experiments. For example, the Gemini Planet Imager is coming online and promises to give us a sample of tens or more of these young gas giants. When people try to count, here's a simulation of what they might see as a function of temperature of the planet versus age. And what they've done here is to assume two different evolutions, hot star, cold star. And you see there's a huge difference. If I look at 10 million years or a few million year old objects, there's a huge difference in the predicted luminosities or here temperature. So you should be able to pick this up. And all the discussion is usually in terms of this bimodal cold star versus hot star possibilities for the evolution of young gas giants. And the idea is that these direct imaging experiments are going to tell us which one is right. So it's really important for predicting yields if you decide to design such an experiment. So what determines that in correlation simulations, right? But again, let's divide this into two parts. Let's try to do an easy part and a hard part. So another question is, what if somebody hands you in 3 years, somebody hands you a sample of 50 cooling gas giants that are 10 million years old, and they've measured the luminosities of them? What does that tell you about the initial entropy? Does it tell you something? Can I work back? For example, if they're all very low luminosity, presumably they're all cold in the beginning. If they're all high luminosity, they're very hot in the beginning. Can I learn something like that?
Lack of knowledge of the max.
I'll show you. I'll show you now. So this is what we've been trying to figure out, and I thought it was interesting. It's quite simple in some ways, but I think it's interesting to show. There's an interesting result for deuterium building, which I'll show you. Okay, so we've been calculating again using the same stepping to radiobats technique. We have the models there. Let's just do it. What's the evolution starting with different entropy? So here you see the evolution, and as I increase entropy, I increase the initial luminosity. And then the idea is that eventually, if I take, say, the red curve and the blue curve here, they're both the same mass. The top red curve here and this blue curve are both the same mass, but they start off with very different luminosities because they have different entropies initially. But eventually, as I wait for a long time, eventually they move on to the same cooling train. So the idea is there's a maximum, for a given mass, there's a maximum luminosity at a given age, which is the hot star cooling train. And if I'm cold, I just come along and jump.
Why do you, sorry, maybe I'm just daft today, but why do you get flat part at the start?
It's flat because I'm making this planet in a condition where its thermal time is 10 to the 8 years. But I've made it in a million years.
Right, I see, okay.
So I have to wait 10 to the 8 years before it starts doing it. So this is just to show, Spiegel and Burroughs came out with a paper also in the last year where they also consider this evolution. The idea is, let's consider the evolution by arbitrary entropy. Let's just say, let's imagine core accretion can give us any entropy we want, or plants can give any entropy we want. Let's just assume that's an input parameter, so I can just vary the entropy arbitrarily. Let's see if I can extract it from the data. That's the context. Okay, so how's that going to work? Oh, well, just to show you, so again, we calculate luminosity as a function of entropy, and we use that to step through a grid. Okay, and it turns out there's some interesting scalings, like this scaling, which is true for irradiated objects. It's also true for isolated objects in a certain entropy range. There are details here, but there's some interesting things I could show you offline. Okay, so imagine if we've measured an object, we've measured its luminosity, and we've measured its age. And obviously there are certainties, but imagine if we've done that. How can we match that with our models? So here I'm showing you two different models which reproduce that data point. And the idea is I could have a hot start solution, which has a mass of 1.85 Jupiter masses, and that cools through here. But the other way to do it is I can make it colder initially and give it more mass. So I can make it 12 Jupiter masses and then entropy 8. And then that object just wouldn't be cooling for a long time. It would just go right through the data. We see it there. And later on it'll join a higher hot star, the hot star for 8 Jupiter masses.
The radius will be different. Okay?
Yes, if you measure the radius, that would distinguish.
But you don't measure radius when you measure band passes, because band
If you could infer, that's right, if you could get some idea from the spectrum. Yeah. I didn't know that. Okay, so what this means is that there's a degeneracy between entropy and mass. So in particular, for that object there, those two curves are the blue point and the red point, this complicated line. So here's initial entropy from 7 to 12. The black circles are the cold star prediction from Mali. And then these curves here are the curves given a measured luminosity, 10 to the minus 7 to 10 to the minus 5 L sun, or different ages from 10 to 100 megayears. So if I measure one data point, I get a constraint which is a line like this in the MS plane. And it's just saying, if I have really high entropy, I don't care that then there's a unique mass, which is the hot start mass. I have to have that mass hot start track to go through the data. Whereas if I go to higher masses, I can always just make it a bit colder and colder, so it hasn't evolved yet and it goes right through the data. So you get these kind of constraints here. And this is, if you take HR 8799, for example, just take those planets, take those in masses and ages, and this is the constraint. So for example, we can answer questions like, how far away from cold star am I? So if I want to modify my core accretion theory, how much exactly do I have to change things by? And I'm not suggesting that HR 8799 planets that are quite far out, but actually the inner one is around 15 AU, I think. The other ones are further out, 30 or 40 AU. So I'm not necessarily suggesting they're formed by co-accretion at those large distances, but if I'm just allowed to increase the mass a little bit from the hot start value, then you can drop the entropy. We can also put a limit. We can say, well, the entropy can't be lower than about 9.5 for these objects. And the other point to make is that for this system, because there are multiple planets, you have a dynamical constraint on the mass, and that's what these lines here are. So the idea is there's an upper mass limit. The mass limit can't be larger than this, otherwise it should be dynamically unstable. There are various studies which give slightly different limits, but they lie between 5 and 7 Joule masses here. So for this one, we're saying actually it has to be, say, on this part of the green curve. So if anything, I think it's evidence that this one was a hot start object. It had to have at least 9.5 and both initially.
Is that close to that?
This is the closest one. Sorry, no, C is the closest, I think. C. Sorry, that's a blue. Which one's the closest one? Is it E?
Well, one of the, right, the last one is the closest.
E, the last one. That makes sense. Okay, so I think that's fine. So we're basically beginning to just answer this question, but one thing I just want to show you here is the interesting deuterium evolution that we found, okay? So you can put deuterium in these very simple stepping to radiobats type calculations in the same way we put ohmic heating. You just say there's some deuterium building luminosity, it's going to be at the center of the object. It's going to be in the convection zone at the center, so we just put it in as a deuterium building luminosity. And we just calculate it across the grid. And so we can evolve these models with deuterium burning. And even with this very simple approach, you can get pretty good agreement with the literature. And then we can start to lower the initial entropy. Now, what if you could make a 13 Jupiter mass object by core accretion? Or what if you could make a 15 Jupiter mass object by core accretion so it's cold? What would happen? And we find these flashes. So what can happen is I have to fine tune the entropy a little bit. So this is 7.5, I think it's 7.7, 7.8, that kind of level. Here we get to about 9. But if the entropy is low, then what happens is you delay the onset of deuterium blending, and you can get these late time flashes. And it allows you to access late time.
So it gets equinonuclear basically burning instead? Why it still burns at all?
It's still thermonuclear.
So it gets hotter over time?
It's getting denser.
So then it's a density effect, that's why I was
So it gives you a way to access, and actually I forgot to add to the slide, but this had been looked at before. Salpeter had these papers in the early 90s, Salpeter and I think Lenzini. And what they were trying to do was explain the galactic dark matter, perhaps as due to very slow accretion. Brown dwarfs would accrete very slowly. So they're asking the question, if I have a brown dwarf accreting really slowly from the ISM, can I avoid deuterium burning? So there's a lot of, so they're working at slightly too high a mass, but there's a lot of interest in
They wanted to avoid hydrogen burning, I think.
They
wanted to avoid just normal hydrogen burning and make something 0.3 solar masses or so, which never ignites.
They wanted to push up the hydrogen burning mass limit.
Yeah, so you get lots of cold hydrogen by torch sort of thing.
But they have a lot of discussion in there about deuterium. So it's interesting to go back and look at this question, I think. I'm not saying we've seen any of these things, but, and this may just be a curiosity. That's the question, can I really make a 15 Jupiter mass object with an entropy of 8 or 7? Can I do that? And that's not clear. And actually, last night on Astrogation, there's an interesting paper by Modesini et al. Actually on this. I haven't had a chance to read it yet. But I had a quick, I don't think they're seeing the flashes, but anyway, I should stop. Let me just show you one more thing. The camera will stop. So here's the collection from Neuhauser and Schmidt, and just overlaying cold start and hot start models. Here's the current sample of direct image objects. And I think there are some very interesting questions one could start to ask here about selection effects in this diagram. Why don't we see things down here? The objects seem to follow the hot start evolution roughly. Are we just seeing hot start objects here? Are we going to eventually pick up some cold start ones, or is there a gap here? There should even be a gap. If you could really sample the density here, there should be a gap here where deuterium burning lifts these light curves, but not these ones. There should be a little gap there. And there happens to be, I'm not saying it's real, just interesting questions. So I just wanted to show that, and I'll just leave the conclusion to probably start.
So what's the conclusion of that? We should go back to the previous slide. What will be your first order conclusion?
I think the conclusion here is
Looks like hot start.
These are all very far out, right? So most people, I think, have suggested that this is basically like a binary star.
they're very far out. Yeah, I had a problem at the very beginning. They're 100 AU type distances.
There's also no mass on here, so how does the mass different tracks with different masses, right?
Yeah.
Oh no, different tracks with different initial.
That analysis is, I'm basically saying, this kind of analysis is interesting to start looking at. I haven't looked, I haven't checked it.
But ignoring
Those tracks are masses from 1 to 20 for the red as well.
So these are different masses.
Oh.
Yeah.
Oh, those are different masses.
So these are different. The red, these are different masses.
Yeah, but
Oh, that's the
range.
mass.
The top one I think is 20. The top one is 20. I think this is 1.
Yeah.
You're saying they're all 20.
Same year.
Yeah.
You're basically saying they're all 10 to 20.
Is that what you're saying, right?
Well, if you believe that.
Well, if you think that it's hot start because of its gravitational stability, then there's a minimum mass associated.
Which is consistent with this theory. So this is all gravitational.
But
What I'm saying is, it'd be interesting to say that statement in a more careful way.
Where's HRA 719?
But there isn't a selection
That's
effect
what-
here because you have a two L over L sun in the companions, right? So, I mean, at 10 to 6 years, you
There's
should.
no reason why you shouldn't have seen kind of 6
Yes.
million little guys. That those
Yeah.
little nuts.
Right.
Yeah, that's true.
Although some of this, for example, is done by looking at specific clusters. It could be that you look at specific parts of the sun.
The young stars are generally much further away, so you have to be a bit careful, right? So they're hard to do.
Sure. So that could be a selection. Well, but that's
Well, of course, this is a very huge range in luminosity, so the fact that clustering the vertical direction is still only an order of magnitude clustering. But on the other hand, your curves are very far apart. So it's,
The point about having a gap because of the flashes, that applies only to cold start models, right? It doesn't apply to hot start models.
Actually,
There's
no,
a little bump.
I'm saying that there's, in principle, if you can sample this space densely, there should be a little gap here, even in hot start, because there's a deuterium mass splitting limit, and that lives here.
And the HRA 799, are those gray forms? Where did they form? I can't see. Do you know?
I'd have to look, I'm not sure right now.
Would they,
I
and
can-
you say those also suggest a hot start?
Yes.
But they probably not gravitational
I mean,
stability because they're resonance.
And that's even a fairly strong statement, just because we have these upper mass limits. I have to lie below 5 or 7 masses. So I'm only allowed to access this part of the green space. So we can put a definite limit, entropy 9.5 or greater.
Well, no, if they happen to be in three-body resonance, they can have much bigger masses.
Okay, so if you allow me much bigger masses, I can make them almost with a cold start.
Yeah, the mass is only because people think about use and so on. If there's a exact three-body resonance, you can hide more mass.
Why would I like to know gravitational patterns?
Well, they are in three-body resonances.
Well, that can happen afterwards. They form gravitational patterns with the gas.
Well, the gas probably have to see in non-mass and then the planets.
They would need all gas. You migrate them into this.
That's true, I guess. I figure
Like rocks.
well, that's true.
Well,
But I think it's quite pushing because it's such a regular system, and there's a lot of reorganization going on, which requires a kind of presentation.
Oh, no, you do that from gravitational classes, right? It's not like the gravitational class. It's really gas disk, and there's no gas disk around the end.
Well,
Anyway, I should
okay,
have
well,
to
it's
over.
less than 100 again.